In this video, we'll talk about finding slopes and tangent lines to parametric curves. Now that we have curves written in the form c of t is x of t, y of t, we now want to try doing calculus on these sorts of curves. We could do it with graphs before, that was not a big deal. We had y plus f of x and could do a bunch of stuff with that from there, that was fine. But what about these sorts of curves? Can I still do calculus on these things? And the first thing we dealt with in Calc 1 was the idea of the derivative or the tangent line. What was the idea of the tangent line we had before? Right, we got the slope of this by looking at the limit as h goes to 0, x plus h minus f of x all over h. That was our formula for the derivative. But where did this really come from? Well, this really came from looking at tiny slopes of secant lines. So really, it was the limit as delta x went to 0 of the change in y over the change in x, because that was the slope of the secant line. The change in y was change between 2 points in y, and then change of x as well. Let's look at this here. Now we have x and y both as functions of t, so we can actually do something with this setup here. And the point here is, using the mean value theorem, I know I can write delta y as y prime of c times delta t, because this delta y here is y of t1 minus y of t0. It's a change in y values at two different points of t. So I can replace that by a y prime of c delta t. I can replace my delta x in the same way by an x prime at d times delta t, where I know c and d are between my two t values. But then this limit becomes pretty straightforward. This limit becomes a limit now as delta t goes to 0, because that's going to force delta x to go to 0, of y prime of c delta t over x prime at d delta t. The delta t's will cancel out. And as I limit delta t to 0, this c and this d are forced to be at the same point, because they're supposed to be between the two t values, but delta t goes to 0 means that all those values become a single value. So I get a y prime at t over x prime at t as what's going to give me the derivative. Another way to think about this is the fact that the derivative is dy dx. And what I get from this thing I said above was this the same thing as taking dy dt and dividing by dx dt. So in a sense, again, we get this fraction thing where the dt's will cancel out. So the point here is, to find the slope of the tangent line, you want your derivative dy dx is y prime over x prime. And plugging in the value of t, remember now in this case everything's a function of t here, that'll give me what I need to find the slope at that point, and I can then use the point x of t and y of t to then give me the actual tangent line. Let's see an example of what this might look like. So as an example, we have the parametric curve c of t is t squared minus 9, 8t minus t cubed. I want to find an expression in terms of t for dy dx, and figure out when the tangent line is horizontal and when it's vertical. So this is just our formula from before. Dy dx should be y prime of t over x prime of t, which I can just figure out is 8 minus 3t squared over 2t. Now, when is this line horizontal? Well, this is when dy dx is 0. Based on what I have above, this occurs when 8 equals 3t squared, or t is plus or minus square root of 8/3. When is this vertical? Well, this happens when the dy dx is undefined. Or if you want to flip it over, when dx dy equals 0. Well, in this case, this just happens when the bottom is 0, or when 2t equals 0, so at t equals 0. If I wanted to find the points for these lines, I can plug them back in. So for instance, for the vertical line, if I plug that back into the equations, I know my vertical tangent line occurs at the point minus 9, 0, because when I plug 0 into my equation, that's what I get. You do the same thing for the horizontal lines as well. So that's the idea of using these parametric equations, these parametric curves, and finding their tangent lines. It's building up this idea of, can I still do calculus with these differently defined functions where they're now parametric and not just straight up normal functions? And the answer is yes, and we can start building up there from tangent lines.